All right, Physics Notes, Unit 16, Chapter 16, Oscillations and Waves. I'm going to start off with waves. And the most important thing, we'll get into the details and then some mathematical representations here in a minute, but the most important thing to remember about waves is that they're a disturbance, a wiggle or a jiggle, that transmits energy without transmitting the physical material. Energy goes from point A to point B without any actual particles going from point A to point B. Good example of that right now is as I speak. When I speak, and there's somebody in the room hearing me, or anywhere hearing me, or as you hear the words from your speakers, there's not air coming from your speakers to your ears. It's a vibration that's coming to your ears. And I'll show you a little video of that in a second. But it's a transmission of energy without transmitting the particles. Now, the medium is the physical material through which a wave travels. For example, water waves need water as the medium. Sound waves typically use air. Air is the typical medium, but sound can travel through water, or yeah, it can travel through water. I mean, dolphins communicate and other whales and things, and you can, hear things underwater. Sound can also travel through solids like walls and steel. Actually, it travels very quickly through steel, but it's not a very good way to send sound, but it travels through liquid, solids, and gases. But air is the typical medium for sound. The wave at a football game, all right, if you've ever been to a stadium or a soccer game, when people kind of go up and down and that wave goes around and around the stadium, the people are the medium. So that's a good example of a wave phenomenon where there's a disturbance that goes around the stadium. But the people, the medium, really go nowhere. They're just vibrating perpendicular to the transmission of the wave, which we need to get to here in a second. There's a couple ways to classify waves. I've kind of already set this up. So there's, okay, I have A and B here. This is a totally separate classification than numbers 1 and 2 down here. So we have what we call mechanical waves. They require the physical medium. Water waves require water. Sound waves require air or some other medium to travel through. Then we have what are called electromagnetic waves. They do not require a medium. Light is a good example of that. Radio waves fill the room you're in right now. You can turn your radio on and get probably 5, 10, 15 different radio stations. They fill that room right now. And in fact, technically, electromagnetic waves are always invisible. Let me come back to that in a second. But, the radio waves certainly are invisible. You can't see those. Light waves, let me talk about it. Light waves, we think they're visible, but they're detectable. Your eyes detect them, but as they travel through the air to your eyes, you're not really, you don't see them as they travel. They're invisible as they travel. Think about that for a few minutes. I'm not going to test you on that, but that's an interesting thought. You can detect them. They fill the room, and they fill the room just like radio waves fill the room you're in. But we can't detect radio waves with our eyes. We can detect radio waves with a radio. Interesting. Think about that. There's red light in the room you're at. But you don't see the red light. You see red things, like a red shirt. I'm wearing a red shirt right now. You see blue things because blue light hits that thing, or a red shirt. It's because red light hits it, bounces off that thing, and bounces into your eyes. But there's detectors that detect all these things. Your retina has rods and cones, as you know. So that's just another thought. But bottom line is all electromagnetic waves are invisible. And they prefer no medium. They don't, in fact, light waves can only really travel through like a vacuum of space, like sunlight gets from the sun to the earth through the vacuum of space. Radio waves go through outer space. All electromagnetic waves like to go through a vacuum. And air is very easy for basically all electromagnetic waves to travel through. But for like visible light, then you are limited. Like you have like clear glass, clear plastics, some crystal structures, like diamonds, but there's not a whole lot of things that our regular visible light spectrum can pass through. Radio waves can pass through a lot more things than visible light. Radio waves can go through walls because you could have a room with no windows and you could still get your radio stations in that room because they can pass through wood and concrete, and steel is a little bit harder for it. But so the bottom line is they don't need a medium, and the medium slows them down. Okay, another way to classify waves is by longitudinal, or longitudinal as some people say. and I'm going to spend some time on this with a couple of videos. But in a longitudinal, the particles of the wave vibrate parallel to the direction of transmission, or the direction that the energy is traveling, or the way the wave is propagating. Those are big words. But sound is really the only example. If I ask you on a test for a good example of longitudinal waves, which I will show you the video of, like I said, in a few seconds here, sound is really the only good example. Then there's transverse waves. That's the way we think of almost all waves. If we were to draw it like you see in this diagram right there, like water waves, the particles of the medium vibrate perpendicular to the transmission of the wave energy. Water waves, light waves, and these are easy to draw. I mean, draw mathematically, and we're not going to get into the details of the math. You may have done that in a math class where you study more in detail the mathematical equation for a sine wave and a cosine wave, which are really the same shape, just shifted a little bit. We're not going to get into all those details right now. I'll show you the math that we're going to do here in a few minutes. It's just basic algebra. You have some terminology, though. You have wavelength, and we're going to use this weird symbol here. It's called lambda. It's the Greek letter lambda, L-A-M-B-D-A. L-A-M-B-D-A. That's wavelength. It's kind of like a backwards H, sort of. And the standard units are going to be meters. I mean, literally, if you could freeze a water wave in the water, the waves are coming in from out in the lake or ocean, you just measure from the top of one crest. This is called a crest. That makes sense. Top of one crest to the next crest, and how many meters that is. You could do it in centimeters, and then convert to meters, or just leave it in centimeters, but meters is the standard. Then you have this called a trough, this low spot. You could also measure lambda along from one trough to another trough. Gives you the same answer. You also have what's called amplitude, which is how far the wave vibrates from the equilibrium or middle location. This middle line, so amplitude is from a crest to the middle or from a trough to the middle, not from the top of a crest to the bottom of a trough. Okay, so yeah, amplitude is also measured in meters. We'll do a lot more with wavelength than we will with amplitude, but A is usually the symbol for amplitude. Period is the time it takes to complete one cycle of a wave or one vibration of any oscillating system, but here for waves, once again, we're going to apply a lot of this terminology to just any kind of vibrating system. Two more vibrating systems we're going to have that are periodic or systematic, cyclical, are a pendulum going back and forth and a mass bouncing on a spring. But we also applied it to like planetary motion last term, the period or how much time it takes to get around the sun, 365 days for the Earth. That's the period of our earthly year. Or the period of our day is 24 hours. Or the period of the moon's orbit of the Earth is like 27 point so many days. So it's the time it takes for the cycle of one oscillating system to complete itself. The standard units are seconds. Then we have frequency, which is just going to be the reciprocal. I'll show you the math in a few minutes here, but it's the number of cycles occurring each second. So we call that cycles per second. It's right there. It's the standard unit, cycles per second. We call that a hertz, H-E-R-T-Z, abbreviated H-Z. I'll do the math here in a few minutes, but I promised you these little videos, so let me pause a few minutes here, or go to the videos. But these videos are on longitudinal and transverse waves and how they're different and how they propagate. In other words, how the energy travels from point A to point B and what the particles in the medium do as the wave propagates. So sound waves are pretty much the only good example of longitudinal waves that we have. And we typically don't draw this because you can't see sound waves. You detect sound waves with your ears. But this diagram right here, there's a tuning fork that I'm going to start the simulation here in a minute. But all these white dots represent air particles. And once again, what you'll see here is the wave energy going outward. In real life, it would be like in spherical direction, in all directions. Even as I talk right now, the sound waves from my mouth the energy goes out in all directions, even behind me. If you were behind me, you could hear me. But on a piece of paper, it looks like circles. But you'll see the energy going out, but every little individual white dot, air particle, really just vibrates forward and backwards. Out and in, parallel to the way the energy is traveling, which is always outward. Now, a couple things about sound waves. These spots where the air particles are compressed together are literally called compressions. So we have a compression rate. I'm in the middle of a compression right there. There's a middle of a compression right there. And if you measured from one compression to the next, that's called the wavelength of that sound wave. You could literally do that if you could see sound waves. You could see the air particles, and you could freeze them in air like this. Or you could measure from these spread apart particles. Those are called rarefactions. R-A-R-E-F-A-C-T-I-O-N-S. Rarefactions. We'll write that down eventually here. But you can measure from that rarefaction to that rarefaction to get the wavelength as well. Now, as you'll learn with transverse waves, which is the way we typically draw a wave, because we see those all the time. Water waves are good examples of transverse waves. One of the best examples. Light is an example of a transverse wave, but it's interesting that we can detect light waves with our eyes, but we really can't see them as they travel through the air. It's a whole another weird thing about them. But for transverse waves, we draw crests and troughs, as you'll see on the piece of paper. You'll see that diagram in a minute here. But if I start the simulation, you'll see the energy go outward. Right, so all the energy is going outward, but any individual white air particle is going nowhere. It's just vibrating back and forth, back and forth, back and forth. So that's the basic characteristic of a wave, this in particular a longitudinal wave. And if I ask you for a longitudinal wave example, just say sound. It's really the only example we have. There's another one or two examples we could use with slinkies, but those aren't even the best. You might have done that in high school. You can use that as an example. But longitudinal wave, the particles vibrate forward and backwards parallel to the way the energy transmits. And once again, the energy is the important thing. The energy is being transmitted, not the particles. The particles have a net displacement of 0. They just vibrate. That's all they do. And this will be using a slinky to demonstrate transverse waves where the energy transmits from point A to point B, from the person's hand to this holder over here on the left. That's the way the energy is traveling. But the particles, in this case the medium is the slinky, so the particles in the slinky vibrate perpendicular to the way the energy transfers. Here we go. All right. And stopping, and then showing you slow motion. The particles go nowhere. They vibrate perpendicular. The medium particles vibrate perpendicular to the way the energy transfers in this arrow, according to this arrow right there, a transverse wave. Quick recap. Wavelength is symbolized with lambda. It's measured in meters. Amplitude is how far you are from the central line. That's measured in meters. Period is how long it takes to make one of the cycles of something that's repetitive. It's measured in seconds. And the frequency is the number of cycles per second. So what that means with period and frequency, let's see if we can get down here. No, this is not going down. Hang on. All right, you got here. So T, period, equals 1 over F, 1 over the frequency. We'll use that equation a lot this year. This is for anything that's periodic, any oscillation, but in specific here it's for waves. What it also means, if you rearrange this, is that F equals 1 over T. It's the same equation. You could write it another way too. You could say that 1 equals F times T. Anyway, these are simple. If the period is 6.3 seconds, calculate the frequency. So I can use either equation. I'll use the one that's the bottom one here. It's the same equation. So the frequency is just 1 over 6.3. So if you do the math here, that is 0.16 seconds. And then it says if the frequency is 23 kilohertz, calculate the period. So watch out for the kilo here. So I'll just use the other equation, the top one. It's the same equation. T equals 1 over the frequency. Now, this is 23,000. Or you could have said 23 times 10 to the third, or 2.3 times 10 to the fourth. Those are all the same. But if you plug that in, you get 4.3 times 10 to the negative fifth hertz. I'm sorry, seconds. Seconds. Looking for the period. So this is a short period of time. Alright, and then you have the velocity of the wave. This is probably the one we'll use the most. We'll use those two, or that equation, quite a bit. But this one here that I just circled, or boxed out, the velocity of a wave equals its wavelength in meters times its frequency in hertz. Once again, you'll have a lot of success with this because it's pretty straightforward. And number 3 here, the musical note C on a piano or any instrument. At room temperature, 70 degrees Fahrenheit is about 21 degrees Celsius. Just straight plug in the velocity, or really the speed, 1.34 meters. Make sure it's meters times 256. And if you do the math here, it is 343. I can go to 3 sig figs meters per second. And it travels in all directions at that speed. And then the musical note A, same temperature, because the temperature, when it gets warmer, the speed of sound speeds up a little bit. We'll make that adjustment at a later date, but right now we're going to assume everything's at room temperature so we can just apply these formulas directly for the moment. Well, V equals the wavelength. Watch out here, the wavelength here is 0.78 meters, 78 centimeters, 0.78 meters, times 440, 0.0, which is 4 sig figs, but the 0.780 would have been 3 sig figs. Lo and behold, you get 343 meters per second. Well, you should notice those are the same, which is good. Because if you're listening to an orchestra that's on a stage, in a room, it's nice that all the sound waves travel at the same speed and get to your ears at the same time. Otherwise, if sounds travel at different speeds, got to your ears at different times, you wouldn't hear the right mixture of all the instruments. So sound waves travel at 343, that's the accepted speed of sound at typical room temperature, 70 degrees Fahrenheit, 21 degrees Celsius. So when they say you're at room temperature, you're going to use that velocity for the speed of sound. That's like just over 700 miles per hour. It's pretty fast. For airplanes, they call that Mach speed, Mach 1. So if an airplane can go faster than Mach 1, it breaks what's called the sound barrier. Talk more about that later. Or if an airplane is doing Mach 2, it's doing twice the speed of sound, twice this number, or 2 times like 700 and something, so it's like 14 or close to 1,500 miles per hour. And there's some jets there, especially military jets, that can go that fast for reasons that's important for them. But commercial airliners mostly are going like 500 to 600 miles per hour. I think more like around 500 miles per hour. Anyways, electromagnetic waves. That's sound waves. Electromagnetic waves, like light, radio, microwaves, all of those waves are really just different sizes of the same thing. They all travel at 3.00 times 10 to the 8th meters per second. That's going to be a very important number to remember or write down or have access to. That's what we call the speed of light. And nothing can go faster than that. Well, there's some theories about the possibilities, and that's fun to think about. But as far as we're concerned, that's the maximum speed for anything. But that's the speed of radio waves, microwaves, infrared, visible light, X-rays, gamma rays, in a vacuum. Air slows these things down a little bit, not much. But for light, visible light, glass slows it down substantially. We'll talk more about that later as well. So we have that speed. So keep those two speeds handy, because if we have problems that are dealing with sound or light, those are kind of assumed that you know those or use those. For example, here, number 5, WGN is, that's where they used to play, the Cubs used to be on WGN. I don't know if they still are on WGN, if you're a Cubs fan. I'm a Detroit Tigers fan, by the way. I'm from Michigan originally, near Detroit, so you can feel, well, don't feel bad for me. The Detroit Tigers have won a couple of World Series in my lifetime. So 1968, 1985. So I was alive twice for them to win the World Series, but it's been a while. What's really bad is the Detroit Lions. Like, they have never won a Super Bowl. That's the longest streak that any professional team has right now for losing. The Detroit Lions. I mean, the Cubs overcame their streak, and the White Sox previous overcame their losing streak. But anyways, don't feel bad for me. And sorry about that digression. But here we go. V equals lambda F. V equals lambda F. We've got to figure out the wavelength for WGN radio waves. The velocity is 3.00 times 10 to the 8th meters per second. That's good. We're looking for the wavelength. Frequency is 720,000. So you can say 720 times 10 to the third, or you can just put it in there. But the kilo means 3 more zeros. 1,000. So you do the math here. That comes out to be like 420 meters. And once again, those waves are in the room you're sitting in, most likely. You could turn your radio on and tune to that radio station right now. That your room is filled with those. You just can't see them. That's a big wavelength from peak to peak. And they're traveling really fast. So why don't they knock you over? Well, because they're not particles. They don't have any mass. They don't need a medium. They're just we'll talk more about it later. They're an electric and magnetic field, which is not a particle. So if a particle is traveling that fast, it would knock you over. If you go back to sound as well, like sound travels at 343 meters per second, so why doesn't it knock you over? Well, because it's not wind, it's not air traveling at 343 meters per second. It's the vibration that transmits as one particle bumps into the other particle in front of it. Air particles, once again, are really going nowhere. They're just vibrating a little bit. They're not going that fast from point A to point B, because if they were going that fast from point A to point B, 343 meters per second, they would knock you over. It'd be bad news. All right, number 6 here. Calculate the period for green light waves. Okay, so this is a 2-step problem. At least 2 steps. V equals lambda F. Once again, it's light, so you're supposed to know now, or remember, with my help at least at this point, if it's light, it travels at that speed, 3 times 10 to the 8th, equals the wavelength. Now, you might have to look this up, but I remember this. This is nanometers. That little n right there is nano. That's 10 to the negative 9th meters. That's the prefix for that one. So this is times 10 to the negative 9th. You have to look that up or remember that from your metric prefixes. Times the frequency. So this will give me the frequency of green light. Green light. And I know it's in the room that you're sitting in, because you can see green things. The green light that's from the light bulbs, because the light bulbs are giving off all the colors, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, and all shades thereof. And that light travels through the room, hits things, and some of it gets absorbed, some of it gets reflected into your eyes, and then you see things the color they are, because that's the light going into your eyes. And you detect it with your retinas, as we mentioned before. But the frequency here is 5.64 times 10 to the 14th hertz. But I want the period. Well, as we learned earlier in this lesson, the period is 1 over the frequency. So if I take 1 over the 5.64 times 10 to the 14th, then the period is a really small number. It's 1.8. I'm going down to 2 sig figs here. 1.8 times 10 to the negative 15th seconds. All right, so that's the period of a green wave of light. Eventually we'll call those photons, and that's a whole other story once again. But right now, get used to this. These computations, you will be doing those for the homework.